Right, sharing screen now.
You can just basically get ready, play away. I'll just entertain you. Bloody part-timers. I know, Daniel. Sorry, man.
Right, give me a minute. I'm just going to go and get me...
One of us has been sat here ready for 20 minutes, Daniel.
One of us has been writing this all up.
Yeah, which means one of us hasn't even seen this presentation. One of us is as much a passenger as the rest of it.
Yeah, I'll be quite surprised. Well, just going to get me clicker. I'll be back.
Do your thing. Do your thing.
So, basic cable calculations, we're literally talking just cable calcs, straightforward cable calcs. We're just going to run through those just as a reminder for those that have been doing it for a while, and just a bit of info for you guys that are a bit new. So anyway, here we go, cable calcs for designs. When we're looking at cables and conductors, there's always a limit to how much current they can carry. If we go over that limit, then we're going to have problems, okay? The limit is due to the temperature that they achieve under load. When we start putting current through a cable, through a conductor, it will begin to warm up. The more current it carries, the hotter it will get. Okay. And there is a certain point where the insulation around the conductor will begin to get damaged. It will start to break down. It will start to go soft. And eventually, if we don't interrupt that current, the insulation will ignite. PVC will burn. Okay, and we have a fire situation. Different insulations are rated at different temperatures. So we've got 60-degree thermosetting, we've got 70-degree C PVC, we've got 90-degree C thermosetting, we've got MI, which if it's bare, we talk about 105 degrees C. There's various other cables all in the wiring regs, in the tables in Appendix 4, with different temperature ratings. So it's the insulation, which is the initial thing that we're worried about. We don't want to be damaging that. If we run the cable too hot, we will cause damage to that insulation. If we run the cable very hot, we may even melt the cable itself. And if you consider in the case of a CPC, yeah, if we melt that conductor, remember if we're using twin and earth, for instance, the CPC is the next weakest link in the circuit. Obviously the weak link is the fuse or the circuit breaker. That's what it's there for. It's there to be like the safety valve for the circuit. If that doesn't operate because it hasn't been maintained, or it's got a fault, or any other issue, we put the wrong size in, the wrong type in, we can have a situation where the cable will overheat to a point where the next weakest link is the CPC. So under earth fault conditions, you'll have this large earth fault running down the line back on the CPC will melt. Once that melts, we're in a world of pain because the conductive parts of the equipment will remain live because we've now broken the safety circuit. Line and neutral conductors normally carry the current, as we know, in the circuit, but under certain conditions, as we've just mentioned, the earth conductor or the CPC will carry current. And we'll consider that later when we look at sizing of protective conductors. Under normal use, the current flowing in the circuit, we can calculate that from the connected loads. And then we call that the design current, IB. So if we've got a 3 kilowatt load, like an immersion heater, for instance, we can simply do the calculation. It's the power, which is 3000. Remember, we're using basic units. So instead of 3 kilowatts, we use watts, the basic unit. So it's 3000 watts divided by 230 volts. We come up with a design current, IB, of 13 amps. And that's pretty basic, pretty straightforward for all of us. Once we know what the design current is, we can then start choosing certain parameters for the circuit. We can select the protective device, for instance. Once we've got the protective device, we can start thinking about what size cable we're going to need. When we consider the variables of the circuit, they're mostly related to current. IN is the rating of the overcurrent protective device. Now, IN should be greater or equal to IB. If we've got a 13 amp immersion heater, it's absolutely pointless putting a 10 amp breaker in because it's going to give us nuisance tripping. Yeah? So we need a breaker which is rated at least 13 amps and probably slightly higher. And we'd normally select maybe a 16 amp breaker for an immersion heater circuit. IB, the design current is 13 amps. IN, nominal rating of the protected device, 16 amps. Then we've got some other things there. IT is the tabulated current carrying capacity of the cable. These are the values that are given in Appendix 4. In Appendix 4 of the wiring regs, BS7671, there are loads and loads of tables in there, 4D, 1A onwards to God knows where, yeah, relating to lots of different types of cable with different types of insulation, with different conductors. So we've got copper and aluminium in there as well. Okay, MI, flexes, all sorts in there. So we need to make sure when we're using table from Appendix 4 that we select the right table for the right cable. IZ, that's the current carrying capacity of the cable for continuous service. And that is where we can include all the installation conditions and the correction factors applied. Okay. Remember, under certain conditions, the cable may heat up to a higher temperature than we would consider normal due to the current it's carrying. And that all depends on things like the ambient temperature it's going to be in, whether or not it's been surrounded by lots of lagging, whether it's surrounded by lots of other cables, and a whole range of other issues where the cable cannot dissipate its heat. So when we're looking at these, obviously the nominal rating of the device should be less than or equal to the rating of the cable. Yeah? If we've got a 20 amp circuit breaker, we don't want a cable which is only rated at 16 amps. The cable rating needs to be at least the same as the device or slightly higher. Factors that affect the cable temperature then. And we've got a whole range of these, and these are all in Appendix 4, again, of the regs. The cable selection process is all laid out there in Appendix 4. It has all the equations, it has all the factors. And you can see this if you read through Appendix 4. We have CA, which is the ambient temperature. Right? We mentioned some time ago that we've done work out in Dubai, and some of you guys have done work in other places. The ambient temperature in Dubai is 45 degrees. That's the actual stated ambient temperature. Yeah, so obviously the cables are already warm. They're not going to take that much to get them to the limiting temperature. So if they're starting off warm, yeah, they're going to heat up quicker. Cables buried in the ground, again, it's harder to dissipate heat. If you're buried in the ground surrounded by soil, it's harder to get rid of that heat. The depth of burial also has a factor. So depending on how deep the cable is buried, there is a factor in relation to cables buried in the ground. Semi-enclosed fuses, CF. If we're protecting a circuit against overload, these are slow to operate. So if we've got a circuit that can be overloaded, then we need to consider the use of semi-enclosed fuses, and we have to apply a factor. Remember, not all circuits can be overloaded. So if we've got things like a immersion heater or a shower, they can't be overloaded. If you consider a shower, it doesn't matter how dirty you are, it's still only going to pull the same amount of current. It doesn't matter how many people are in the shower, it's still going to pull the same amount of current. Okay, so you can't overload a shower. If you've got a socket outlet circuit, you can overload that by just keep plugging stuff in, keep more and more equipment plugging. If you've got a motor, you can overload that. If it seizes, if you put too much weight on the motor, too much load on it, it will draw more current, so it can overload. So there are certain circuits that can overload, and there are some circuits that cannot overload. If a circuit can be overloaded, we need to consider, if we've got a semi-enclosed reliable fuse, we need to apply a factor. Now, if you haven't got a circuit that overloads, we can actually ignore that one, because then all we're looking at is fault current. Yeah, under fault, an earth fault or a short circuit, we get a much higher level of current going, and so the semi-enclosed fuse will operate fairly quickly. Right? So it's only where we've got overload conditions that we need to consider the semi-enclosed fuse. CG grouping. Again, think about the penguins in the Antarctic. They're all huddling together to keep warm. If we've got lots of cables all huddling together, they're going to keep warm. the cables in the middle especially are going to be going to find it very hard to dissipate their heat. And then finally, things like thermal insulation, CI. Okay, middle of summer, you don't really want to wrap yourself in an overcoat. So if you consider the cables up in the lofts and in walls where you've got thermal insulation all around them, they cannot get rid of that heat. Okay, so we need to apply a factor there. So those are the main, there's a few more, but those are the main factors that you see mentioned in the regs. And what we need to do is we need to think about how we've installed the cable, what methods we've used, what environmental issues there are. You know, have we got thermal insulation? Have we got a high ambient temperature? Have we got things buried in the ground? And we apply the factors that are needed. Only the factors. We don't apply all of them, just the ones that are present. Where do we find these factors? Well, CA, the ambient temperature, is taken from Appendix 4. It's table 4B1 on page 394. Okay, there's a table there, table 4B1 for ambient temperatures. If it's 30 degrees, the factor is 1. In other words, 30 degrees has no effect. Yeah. If it's colder than 30 degrees, it actually improves the current carrying capacity of the cable. So the factor is more than 1. If it's warmer than 30 degrees, then that gradually derates the cable. The higher we go, the higher the temperature, the lower the actual factor. So we go from 1 down to 0.9 or 0.8, 0.7, okay, and further. So the hotter it is, the worse that factor is. CC, the cable's buried in the ground. That's also taken from Appendix 4, Section 4, page 377. CD, the depth of burial, is in table 4B4 on page 394. The semi-enclosed fuses, there is a factor taken, it's always 0.725. And again, that's taken from section 4 of Appendix 4 on page 377. There's a section there which talks about overload protection. And it mentions in there the semi-enclosed fuses and this 0.725 factor for overload protection. If it's not a circuit that can be overloaded, we can ignore it. CG for grouping. This is taken from table 4C1 on page 396 in Appendix 4. Okay. And with all of these CA, CG, the actual method of installation has an effect. If we've installed it method C, method E, method F, method B, this will have an effect on the factor that we select. And we'll look at these different methods in a bit. And the last one is thermal insulation. Well, this isn't actually in Appendix 4. This is taken from Regulation 523.9, back on pages 143, 144. Okay, and that basically states that if we're running a cable through thermal insulation for half a meter or more, yeah, then we need to derate the cable by half. If the distance traveled through the insulation is less than half a meter, then we go to table 52.2. And this is a major problem because, let's face it, we run cables around lofts, yeah, and then sometime afterwards they get re-insulated or the insulation gets topped up, and the guys that come in and do the topping up of the insulation quite often don't even bother cutting the rolls of insulation down into little sections to go in between the timbers. They actually run them the other way and take the full length of the roll. Yeah, so you end up, it's like wading through sheep when you go through some people's lofts. Not that I've waded through sheep, but there you go. Yeah, so it has an effect on our cables, and we're not always aware of that because this has happened, this has been installed after we've been there. So it's a bit of an issue. So those are the correction factors. Let's say the methods of installation. We'll look at different methods of installation. If you look at table 4A2, which starts on page 386 of Appendix 4 in the regs, and there's quite a few different methods, yeah, that are listed. And they're numbered. I think they go up to 70 odd, yeah, although not all the numbers are included. So I think there's only about 50 to 60 of these. But more importantly, they're given a reference, a letter, and the letters range from A to G. And a lot of them are repeated. So for instance, here we've got number 4 is non-sheath cables in conduit, and that's method B. Okay, well, multi-core cables in conduit is also method B. Non-sheath cables in trunking is also method B. Multi-core cables in trunking, also method B. So there's a number of different methods there, which actually all end up as the same reference method letter. So when we think about, as I say, cables in conduit, we've used method B. Think about singles in trunking, okay? And as we've said, that's also method B. Cables clip direct. We know what that one is, okay? If you look through, you can see it's actually number 20, and that's method C. Now, quite commonly, that gives you the maximum current carrying capacity of cables. If you look at the clip direct value for most cables, that is the maximum they will take, but not always. Be careful, because if you look at cables that are actually put onto perforated tray, they will actually carry more, because the perforated metal tray helps them to dissipate heat. So don't always assume that method C gives you the maximum current rating of a cable. It doesn't. There's an additional bit to that table, table 4A2 continued, on page 390. And this is particular to flat twin and earth cables installed in thermal insulation in 2 situations. One is up in the loft, and the other one is in stud walls where there's thermal insulation applied. And there are these 4 methods. 100 and 101 are for cables in lofts with thermal insulation over the top, depending on the depth of the insulation. 102 and 103 look at cables within stud walls with thermal insulation applied. 102 is where the cable is actually contacting the outer skin of the wall, or the inner side of the outer skin of the wall, the actual plasterboard. And 103 is where there is no contact with the plasterboard at all. And this is commonly where most people, a lot of people, run their cables. They want to keep it away from the plasterboard, thinking about nails and screws going in and damage to the cables. Well, actually, this has a detrimental effect. And we're actually better off putting the cables in where they're touching the plasterboard. For these 4 particular methods of installation, we refer to table 4D5. Okay, so a particular table in Appendix 4, and we get the current carrying capacity of the cables from that table, table 4D5, for these 4 methods of installation. So if we look at a cable above a plasterboard ceiling with up to 100 mil of thermal insulation, then we're looking at method 100. When we refer to table 4D5, we will refer to that method, method 100. So let's look at these tables individually. Well, CA is the ambient temperature table. This is on page 394. We've got different insulations there: 60-degree thermosetting, 70-degree C thermoplastic, 90-degree C thermosetting, and MI cable. We've got the temperatures there on the left-hand side. That's the ambient temperature, and we select the correction factor by looking across to see, well, that's the insulation type that is used on our cable. At that ambient temperature, that's the factor. So for instance, a 70-degree C PVC cable at 35 degrees, we're looking at a correction factor of 0.94. Okay, so when you look at that table, what about a 90-degree C XLPE thermosetting at 40 degrees? What is the correction factor for that? Okay, so we've got the 40 degrees down the left-hand side. We run our fingers across to the 90-degree C thermosetting column, and we can see that we've got a correction factor of 0.91. That's our CA for that particular cable in that particular insulation with that ambient temperature. What about a 70-degree C at 25 degrees, a cooler ambient temperature, we've got 1.03. So effectively, if you had a cable which could normally take 10 amps clip direct in the open air, okay, if you installed it as per number 1 there at 40 degrees, it could now only take 9.1 amps. If you installed it as in number 2 at 25 degrees, it can actually now take 10.3 amps. Okay, so the lower temperature actually increases the current carrying capacity of the cable. So if you're wiring up in the Arctic, yeah, you'd be doing okay. When we look at CG for grouping, this is taken from table 4C1 on page 396. Okay, so again, we're looking at the reference methods. You've got the reference methods down the side there, but it's quite a bit confusing because you've got method C, you've got method E, but the top is actually methods A to F. Well, doesn't that include C and E? Well, yes, it does. So really what you want to look at is on the left-hand side, the top row is for cables which are bunched in air or on a surface, embedded or enclosed. Well, enclosed could be in conduit, could be in trunking. Yeah. So that would include obviously method B. So that would be that top row. A single layer clipped on a wall would be the second row down, method C. Okay. So pretty much we're going to use the top row unless it is particularly method C or method E. So for 3 circuits, for instance, in a conduit, now in a conduit is obviously method B and it's enclosed, so we're going to use the top row. 3 circuits in a conduit, we're going to use 0.7. So what would 4 circuits in a trunking be? Okay, so again, we're going to use the top row because it's in a trunking. It's still enclosed. It's method B, which is included in A to F. So we're looking at 4 circuits, 0.65. Our CG, correction factor, 0.65. What about 2 circuits on a tray? Well, on a tray is the 3rd row down. Yeah, on a perforated horizontal or vertical tray, it's method E. 2 circuits on a tray, 0.88. Okay. The other thing to consider about this is that if your circuits carry less than 30% of the grouped rating, it can be ignored for the purpose of grouping. So if you know for whatever reason that your design current in your circuit is less than 30% of the group rating of the actual cable that you've selected, yeah, then it can be ignored for the purposes of grouping. Again, we're looking at overload. Considering overload, I've got a little graph there. Here's a circuit. The nominal rating of the device, IN, is the orange line, the orange dotted line. The design current, IB, is the green dotted line. Yeah, as we can see from here, the design current should be less than or equal to the nominal rating of the device. It's no good having a design current higher than the rating of the device because it will give us nuisance tripping. And there we see in red, we've got the circuit. It's got its socket outlets, yeah, and we've had people gradually plug in more and more and more equipment in. And we can see how the current increases in stages. It gets up to the design current. It gets up to the nominal rating of the device. It goes past that because we're plugging more bits of kit in, and it gets higher, and it gets higher, and it gets higher. And overloads can exist for a substantial amount of time. Okay? Eventually it will go, but it takes a period of time. So the trouble with overloads is the time duration of them. During that time when they are overloading the circuit, these currents are going to heat up the cables and they're going to stay hot. Okay, and the trouble with overloads is that we can increase them and increase them and increase them as long as we do it gently. And in the case of reliable fuses, which I think we've got a fusing factor of approaching 2, we can almost get double the amount of current through the circuit before the rewirable fuse gives up. Okay. Because of that, under overload conditions, using rewirable fuse BS3036, we have this correction factor for that particular type of fuse, 0.725, whenever that is used on a circuit and is providing overload protection. So the circuit must be able to be overloaded. Now, there's another thing we can do when we're doing cable calculations, and not everybody does this, but it's what they call a preliminary step, which is to do a quick calculation of what the maximum value of volt drop can be for our cable. If we know the length of the run and we know what the permissible volt drop is, and again we get that from Appendix 4, it's 3% for lighting circuits, which is about 6.9 volts on a 230 volt system. It's 5% for all other circuits, which is 11.5 volts. Okay, and there's a table there in Appendix 4 which gives you those values. So if we divide the permissible volt drop in millivolts by the design current and the length in meters, we can work out what the maximum volt drop on the cable should be. So just to explain that, if we've got a 3 kilowatt heater pulling 13 amps, that's the design current, and we've got a 40 meter length of run. Okay, if we take the maximum volt drop, which is 11.5 volts, so that's 11,500 millivolts, and we divide it by the design current and the length of run. So we've got 13 amps, so we've got 40 meters. We do the calculation, that will give us the maximum voltage drop factor for the cable in millivolts per amp per meter. If when we do our cable calculations, it highlights a cable size which has got a volt drop value which is under that, yeah, then that cable is okay. If, however, the volt drop value for the cable we're selecting is over that value, then we can ignore that and go to the next size. Okay, so when we select the initial cable size, it's pointless selecting anything with a volt drop higher than what we've just calculated. Okay, so we'll see how this works later on. So if we're going to determine the cable size to be used, if overload protection is afforded, again, this is all in Appendix 4. This is equation 2 in Appendix 4. We use IT, tabulated value of current, should be greater than or equal to the nominal rating of the device, yeah, because we've got overload possible in the circuit, divided by the correction factors. Any factors that don't apply, just ignore them and drop them out. Yeah. If overload protection is not required because we've got a shower circuit or an immersion heater, a circuit that cannot be overloaded, we can use the design current instead of the nominal rating of the protected device. So in this case, the equation becomes IT, the tabulated value of current, is IB divided by the correction factors. And that is equation 5 in Appendix 4. So IN, when we can overload the circuit, IB, if we can't overload the circuit. And it makes a difference. Let's do an example. We've got a circuit, it's 70 degrees C thermoplastic, PVC, twin and CPC cable. So a standard twin and earth with PVC insulation. It's 40 meters long. It's protected by a standard MCB 60898 type B. The load supplied is an immersion heater. It's a 3 kilowatt immersion heater. The cable is to be partly clipped direct on its own. So part of the cable route is clipped direct and partly installed in PVC trunking with 2 other circuits. The ambient temperature is 35 degrees C throughout. Okay. This has got 2 methods of installation. We've got method C, clip direct, and we've got method B, enclosed in trunking. What we need to look at is which is the worst case scenario, which gives us the worst cable rating. Okay, and if we look as such, method B, enclosed in trunking, gives us a lower cable rating. So we're going to use method B. Select the protected device, the nominal rating of the device, IN. Well, we can take the design current. It's the power divided by the voltage. The design current is 13 amps. So we select a circuit breaker of 13 amps or slightly higher. Well, we're going to select a 16 amp because 13 amps are not common. You do get them in caravans, but they're not common. So we're going to select a 16 amp. So IN is now 16 amps. Select the equation considering overload protection. Well, the circuit can't be overloaded, so we're going to use that one there, using IB divided by the correction factors. We now put in our correction factors. We had an ambient temperature correction factor of 35 degrees, so we selected CA 0.94. We had 3 circuits in the trunking, so we had grouping in there, and we select that from table 4C1, CG equals 0.7. There are no other factors, okay? So we apply those 2 factors, and they occurred at the same time. They were happening at the same time, so we have to apply them both. Put them into our calculation, so IT should be greater than or equal to IB divided by CGCA. So this now becomes 13 amps divided by 0.7 times 0.94. Work that through, it's 13 divided by 0.658. So effectively, IT, the tabulated value of current, is 19.76 amps. So we now need to select a cable that will actually carry 19.76 amps. Not because it is carrying 19.76 amps, but it's heating up. Yeah, the heat factor is such that it heats up to the same sort of degree as a cable that will be carrying 19.76 amps. So we need to select a cable that will actually tackle that. If we go to the cable tables, these are in Appendix 4 again. We're going to go to Table 4D2A, which is a multi-core 70 degrees C thermoplastic insulated and thermoplastic sheathed cable, twin and earth. Yeah. Now, if we were using a cable in stud wall with insulation inside it, method 102, 103, or if we were using a cable in a loft in the ceiling, method 100 or 101, we would have gone to table 4D5. But we're not. This is a twin and earth in a bit of trunking, yeah? There's no mention of the other stuff, so we're using table 4D2A. It's a 70 degrees C thermoplastic, copper conductor, so we use this table. So we look down here, we've got method B, which is in trunking. It's a single phase, so we're going to use column 4. And we look down there, and the first one we can see is a 23 amps. Yeah, that's bigger than 19.76, 23. So we're going to select a 2.5 cable. It's method B, it's single phase. So we select a 2.5, which carries 23 amps. Now then, that's our selection. Well, let's go back to what we said earlier about our preliminary step. In this occasion, we've got a 13 amp, we've got 40 meter run. Yeah, the maximum volt drop on the cable that we've calculated at our preliminary step was 22.1. Anything higher than this, then the cable would not be suitable. So let's check the volt drop using table 4D2B. The 2.5 has a volt drop of, if we look there, 2-core single phase AC, column 3. Well, 2.5 has got a volt drop of 18 millivolts for every amp that it carries for every meter that it runs. 18 millivolts. That's under our preliminary calculation of 22. So that cable is suitable. So we select that cable. We now calculate the volt drop. We put it into the volt drop calculation. We've got 18 millivolts at 13 amps running for 40 meters Okay, remember it's millivolts, so we have to divide it by 1,000 to get the answer back to volts. So the total volt drop is 9.36 volts. And what we can say, therefore, is that the 2.5 cable is suitable for our use on this occasion. Okay, I'll just give you a moment to look at that and to gives me a chance to slurp your tea. So the process is determine the reference method of installation, determine your design current, IB, and select your protected device, IN. Consider whether overload protection is required and select the correct equation. Select the factors that apply and get the values. Apply your factors to the equation you've chosen and determine your value of IT. Once you've got IT, select a suitable cable size, making sure you use the correct table. Once you've got your cable size, obtain your voltage drop rating for your cable and compare with your preliminary calculation. If suitable, carry out your actual volt drop calculation, compare with the maximum allowed. We know it'll be okay because we did the preliminary, okay, and that is now your cable that you should be using for that circuit. So that's the process. Okay. Now, as David will tell you, all this will go probably onto his YouTube channel. So for you guys who are thinking, oh, that's might be useful, yeah, it'll be available on his YouTube channel, and no problem with that. Yeah.
They're probably going to make some more content based on some of the questions asked as well. So yeah.
Yeah, I'm not looking at the questions at the moment because I'm concentrating on the presentation. Yeah, we can go back over some in a bit, but yeah. Yeah, but there's lots of things that you've got to consider with this. So I dare say there's a load of questions. Okay. All right, so let's look at another one. We've got a circuit. This time it's in 90° C thermosetting XLPE, an armored cable, 30 meters long, protected by a 61009 RCBO type C. It's a radiant heater rated at 4 kilowatts. The cable is partly clipped direct on its own and partly installed on a perforated tray with other circuit in an ambient temperature of 30 degrees. The cable will pass through a dividing wall containing thermal insulation, approximately 100 mil thick. So there's quite a lot of information there. So when we think about the method of installation, this has actually got two methods of installation. It's got method C, clip direct, and it's got method E, F on a tray. So which one do we use? And as I said before, we go by the one which gives us the worst case scenario. Okay. You might sometimes end up doing two lots of cable calculations if you're not sure, yeah, which is a bit of a pain, yeah. But generally, we'll go by the worst case scenario. The worst case scenario here is method C, and if we refer to table 4E4A, yeah, which is for the armored cable XLPE, we will see that the current can capacity on a perforated metal tray is actually slightly higher, and that's because the perforated metal tray helps to dissipate the heat. It acts like a heat sink. So clip direct in this case is slightly worse. Select our device, IN, so it's a 4 kilowatt load at 230 volts, so we've got a design current, IB, of 17.4. We can select a 20 amp, that should be RCBO, shouldn't it? So IN, nominal rating, is 20 amps. Select the equation considering the overload protection. Well, the circuit cannot be overloaded, so again, we're going to go with IT is greater than or equal than IB divided by the correction factors. So the applicable factors, well, we've got grouping, we've got two circuits on the tray. So again, if we look at the table 4C1 for grouping, we will see that 2 circuits on a tray, we're looking at 0.88. CI going through thermal insulation, from table 52.2, backed by regulation 523.9, cables going through 100 mil of thermal insulation, the correction factor is 0.78. Now the issue here is one to think of, which is, does the tray continue through the wall? Or does the tray end and then the cable go through the wall in air, as it were, and then go back onto tray the other side? If the cable tray stops and the cable goes through in air, then CG, the grouping factor, would be 0.8. Going through that wall. So these are the things you've got to consider. You've got to consider what factors apply in what position of the cable route, and always go with what is the worst case scenario, the worst combination of factors that apply at any one single point. If you've got ambient temperature at one end, you've got grouping at another end, and you've got thermal insulation somewhere else. If they're acting at different parts of the cable, you don't put them all together. You only apply the factors that happen at the same time, and then you're looking for the worst case combination. What I've done with this one is we've got a grouping factor of 0.88, and we've got a thermal insulation factor of 0.78. Okay, and we've come up with a value of IT of 25.36 amps. So we need to select a cable that will take 25.36 amps. Using table 4E4A, which is a multi-core copper conductor, 90 degree C, XLP thermosetting, okay, we select a 1.5. That's a surprise, isn't it? Because being XLPE, 90 degree C thermosetting insulation, it's got a higher rating than PVC. So in this case, looking at reference method E, we can actually select a 1.5 cable. It takes 29 amps. But if you remember our preliminary step, when we looked at the volt drop, if we do our preliminary calculation, 4 kilowatts, 17.4, 30 meter run, well, 11,500 millivolts divided by 17.4 times 30, 522, gives us a maximum volt drop rating of 22 millivolts per amp per meter. If the cable we've selected has a voltage drop rating higher than that, it's no good. Well, if we look at the volt drop table on the next page for that cable, a 1.5 drops 31 millivolts for every amp for every meter. So we know that cable's going to be no good. So we're not even going to bother doing the calculation. We're going to go on to select the next size up. So we select a 2.5. This has got a volt drop of 19. Okay, go back to there. Well, maximum was 22. We've got 19. Well, that fits our MO for that. We do the calculation. We've got 19 millivolts per amp per meter, 17.4 amps at 30 meters, divide by 1,000. Total volt drop 9.92 volts. Maximum volt drop, remember, is 11.5 volts for other circuits, 6.9 volts for lighting. So the 2.5 is suitable for use for this circuit. Okay, so that's a couple of cable calculations, and there's all sorts of other scenarios we can run through. But I did want to, I've already gone over time, fantastic. I've lost my bet then. I did want to just quickly look at the sizing of protective conductors and using the adiabatic equation. So we're going to do one of these. Sizing of protective conductors, this is in 54 of the regs. Under certain conditions, obviously, as we said earlier, the CPC, or the earth conductor, will carry current under earth fault. When we're looking at selecting the size of a protected conductor, there are two approved methods. Select from table 54.7, where we select in association with the line conductor of the circuit, or we calculate using the adiabatic equation. Now, obviously, the simple way is to just go by the table. It saves you a lot of calculations, a lot of maths, but what you'll end up doing is putting in a conductor which is larger than it needs to be. Now, that has got issues. If you are, for instance, rewiring an installation where you've got trunking and conduit already installed and you want to reuse that, then you may be, by using the same size CPC as the line conductors, you may end up filling your conduit and trunking to overcapacity. Whereby if you use the adiabatic equation and you can select a smaller CPC, it might save you the space required to get the circuits in that you need. So that's just one consideration. There's obviously other factors as well, cost and everything else, but that's just one practical factor where doing the adiabatic equation and selecting a smaller CPC for all of your circuits may actually be advantageous. So when we look at the adiabatic equation, S, what's S? S is the size of your protected conductor in millimeters squared. So that's the size we're looking for. I is the value of the earth fault current. That's the current that's going to flow under earth fault conditions down the protected conductors. T is the operating time of the protected device at that value of current. How quick is the device protecting your cable going to operate under that fault condition? K is a factor which takes in consideration all the different physical aspects of the conductors, the resistivity values of the conductor, the temperature coefficient, the heat capacity of the conductor material, what temperature it started at, what temperature it's finishing at, the upper limiting temperature. So that's all involved in this K factor. And K can be found from tables 54.2 to 54.6 in part 5 of BS 7671, page 197. Okay, and it all depends on how your cables run, what you're using for a CPC, and all sorts of things. Okay, so you need to select the right cable from the right table. Yeah. So if we've got a circuit which is 70° C thermoplastic PVC singles in PVC trunking, it's 40 meters long, we're rewiring it. It's protected by a 20 amp 608 type B. It's an immersion heater 3 kilowatt. The conductor's selected a 2.5, that's what was wired in before. The earth fault current has been calculated at 245 amps. Okay, now this can be done by calculation of what the conductor sizes are, the conductor lengths, taking into consideration what the external earth loop impedance is, so what the likely earth fault current is going to be, can be calculated. We've calculated at 245 amps. Is the CPC adequate if we put in a 2.5? Okay, so we've got a 2445 amp fault current. If we go to Appendix 3, we can find out what the operating time is. And when we go to figure 3A4 in Appendix 3 for the Type B circuit breakers, yeah, it's a what size is it? 20 amp. Okay, we know that a 20 amp Type B takes 5 times the normal rating for it to disconnect under fault. So 5 times 20 is 100. Anything over 100, yeah, would give us an operation time of 0.1 seconds. And we can see there by the graph that that's exactly what we've got. It's 0.1 seconds, the operating time of that device. So T is 0.1. Going to our K factor tables, we're going to use table 54.3, right? Because it is a cable which is bunched with other cables. All right, it's PVC insulation, 70° C. Okay, so we're going to use 115. It's a copper conductor and it's less than 300 mil. So you've got 115 or 103 there. Well, 103 is for anything above 300 mil. Well, this isn't, it's nowhere near it. So we're going to select 115 from that table. We've now got the information we need, so we start putting the information into the calculation. Okay, So S equals the square root of, and we've got 245 squared multiplied by the disconnection time. Yeah, we do that calculation first. 245 squared multiplied by 0.1 is 6002. We take the square root of that, which is 77.5, and we divide it by 115. And we come up with a size of 0.67 millimeters squared. Our CPC needs to be at least 0.67 millimeters squared. We've actually selected a 2.5 CPC, so the CPC is adequate. Okay, so that's a quick calculation using the adiabatic equation. All right, that's still overrun, still going on, but that is the end of that. Are there any questions, David, that we need to tackle?
There's some of the guys have been helping out. David started off by asking about a standard that's referenced in Appendix 4. I've got access to the standard, and it does mention the CMIN, and I see Peter's also mentioned it later on. I have answered the question as to where the CMIN comes from originally to that standard, 50480. As to whether it's useful, there is lots of useful information in there. I could probably send you a message with some of the key criteria in there. It's got good bits of information about line to neutral short circuit currents with stands and things like that. It's just over complex formula, really. There's just lots of formulas, but it's interesting. But it would be too much for us to compress and explain here. There was a question about the RX Z values of the Voltop tables, which I think David or somebody has answered, being obviously, you know,
for larger armored cables, looking at.
Did you want to explain the reason why there are different values?
The resistive, inductive, and reactive, that sort of stuff. Yeah,
different components, obviously. Without going into drawing vectors.
It's looking at the impedance under different sort of components of the circuit. Yeah. Looking at inductance, reactance, and stuff. So, and resistive. So.
Okay, let me just tick off that.
It's all to do with AC theory.
Yeah. There's a question from Ben, which I want to do right at the end, because it's not really on the scope of this, but it's an important question I do want to ask. Now, David came up with another one. Soil thermal resistivity.
Yeah.
How do we quantify it? I get asked this question a lot when I do 18th edition courses. There is a specialist company that back when I first saw this, I had to do some research. I just did a simple Google check, but there's an IEC standard, or is it an IEEE standard, one of the two. But I've got a couple of websites that I go through that cover this. There's an underground power article on a website. I'll put some links into this, but on ictinternational.com, which explains the importance of water content and all that stuff in the ground and how we measure it. But then there's companies, if you do a simple Google, there's Soil Environmental Services and there's soil thermal testing.co.uk that tests soil thermal resistivities prior to cables being in. They actually have lots of good information about the science behind it and where those values come from. Do a little bit of Google searching and reading on those sites. A good one is ictinternational.com. They've got a case study, underground power cable installation, soil thermal resistivity. I can just put.
The problem is we get to the stage where we're looking at the thermal resistivity of soil. So we're then just sort of trying to decide, okay, are there charts, are there tables, is there information? Then you've got to look at what is in your soil. Is your soil this? Is it that? Is it something else? Then you end up sending your soil away for chemical analysis. You know,
the problem
this is the issue that we're getting as electricians. They're giving us this information, you know, and how the hell are we supposed to apply that? Because we're not chemists, you know.
David's just confessed he's the reason we never get in 45 minutes, and he's blooming right.
You are, David, but well done.
Yeah, it's true though. When those of us who actually want to try to again level up, whatever, when we're told it's this, we want to know why it's this. We want to know why it's important to do that, because then we know to keep doing it instead of forgetting it. It's the same with the C-min and the C-max. There's mention about the C-min being 0.95, and there's also it's actually 0.94, but they consider it not to be realistic or reliable. We've obviously seen the C-min. We've also seen now C-max mentioned in the 722 of 7671 because of the potential higher voltage to create a higher touch voltage. So this knowledge of C-min and C-max is important. And so this, I'll try and reference some articles as to where it comes from, but there's been some good chat covering that. So let me just tick that one off. And that one. Okay. All right. David Graham says, who classifies ambient temperatures for countries?
I don't know. All I know, it was in the standard, wasn't it? It was in the wild standard for Dubai.
In Dubai, the way Dubai worked is they kind of copied BS 7671 16th edition. They pasted it. They added color images. They added some content from the on-site guide into it to make it a much
very
more
pretty, actually,
illustrative document. But then, under the municipality of there, was it DIWA, which is the Electricity and Water Authority over there?
Yep.
It's a free download.
Yeah. Oh, yeah.
So when we went over there to deliver training, we looked ahead. We went, oh, here we go, free. And it's like the regulations are free. And we saw most of it is the same information, 16th edition, but things like the ambient temperature. And I guess that would be down to local utilities, local authorities would then make those tweaks.
It was the same with Abu Dhabi. They had the wine regs as well, didn't they? That was quite nice as well.
Yeah.
Very pretty. Yeah,
completely different arrangement over there, and it's all free. But it must be down to local. I mean, I should imagine there'll be some kind of template on an IEC standard, but these things are localized.
This is always a classic question, isn't it, about lofts? What's your ambient temperature up in your loft? Well, if you go up there in the middle of winter, it's bloody freezing. Yeah. You go up there in the middle of summer, it's like an oven.
Yeah.
So your ambient temperature in your loft is ranging from minus something or other to some ridiculous value, and this is one of the issues, isn't it? What do we allow under those conditions? It's crazy, Do we look at the full range, or do we just go for the worst case scenario and say, well, actually, at certain times of the year, your cables up here will be at this temperature, and you think, well, it's crazy.
Yeah. Mark says, when most of the current carrying capacity on H07 is always single phase or three phase AC, single core or multi-core, how would you rate that for DC use?
I would go to is the specification available on the net?
I've not looked, but I should imagine the manufacturer would have that.
Yeah, a lot of the cable manufacturers will have a specification, their own actual cable specification, which they'll have on their website. And I quite often go to those for more exact figures, because the figures in the IET guides and the wiring regs are sort of fairly basic. They're fairly sort of general. But if you go to the cable manufacturers, you should get a much closer, much better, more information from their actual specification for their cable, and hopefully it'll be on there.
Yeah, no, they'll have the voltage range, and they should have the nominal voltages of single three phase AC and DC. That data should all be there. So we can't recommend anything better than check the specific manufacturer really for that one. Jack, what if you have more than 20 circuits, such as in trunking?
Okay. Again, it's one of these things where you come back to using your own skill, judgment, and expertise. Are you going to when you look at quite often at these cable ratings and correction factors, you get to a point where you think, actually, this seems a bit excessive.
It is.
So you would look at what you've got and the actual running parameters of the actual circuits and the patterns of the circuits, and you might decide, hang on, some of these are not going to be running at the same time. There's going to be a certain amount of almost like a diversity, of that, because certain circuits are not running at the same time. So sometimes you just look at the whole thing and you think, actually, when I take a holistic point of view on this, I think I can alter that cable rating down to such and such. And as long as you record that and you actually lay that out on an assessment and say, well, this is what I've done, then nobody can argue with you. Use your own skill and judgment. But when you get up to 20 circuits, it gets ridiculous. If you start trying to apply factors.
If you go, 20 circuits, look at the fact that, they must all now be this, you're immediately going to be wasting time, money, and effort. Because I did a video that I put on YouTube, which some people hated, some people like. Because obviously a lot of electricians zip tie their cables nice and tight to make the board look great, and it looks great. But that's the point. That's completely different to having cables resting in a board, even if the weight is on top, because there are gaps there are air gaps, there are air pockets. And the only reason I made that video was mainly to say, look, has the designer considered that method of installation with that? When you throw cables in trunking, they're not all going to be under full load. They're not going to be under full demand at the same time. And there's going to be air. It does say in the notes under table 4C1 that you have to have, I think, 2 times the same size, 2 times the diameter of the conductor difference between them. Then it's no grouping. Also, do bear in mind that that is for uniform. So the same cable sizes. Okay, there are notes if they have different resistivity. So you may have obviously a thermosetting and a thermoplastic. Those have different limits. You always go for the lower capacity. But if they're uniform, if they're not uniform, there's a regulation a few pages before it. 2.3.3, I think. There's a formula. CG is equal to 1 over n, and 1 over the square root of n, and n is the number of circuits. And if you had like 6 circuits, 1 over the square root of 6, I think it's like 0.4 or something. So the factor's worse. So the recommendation is try, if you do group circuits, to group them uniformly. So, you know, keep the big ones with the big ones and the smaller ones with the smaller ones. If we follow the specific guidelines, we follow the accurate data, we'll realize how blown up it can. And that's why Phil just said it really is down to us also applying our understanding on the utilization of those circuits. You know, you may have circuits, but they may be on very subtle demands, very intermittent demands. They may be on full whack, and that completely changes the landscape of grouping. So you've got to have a good understanding on the use of the system.
Mark's asked whether I would normally recommend getting rid of the BS3. Yeah, normally I would, but for calculation purposes and for exercise purposes, that's why we were sort of talking about them. Yeah, normally if you see BS3036, by all means, you know, you'd recommend to the customer, you know, these are not quite as good, and especially obviously if you need RCD protection, you're going to end up putting RCDs external to the board. So yeah, my recommendation always would be, yeah, I think you need to think about changing these. But then if they haven't got the money, am I going to do it as charity?
This is the point that we mentioned this a couple of webinars ago. I lose track of which webinars we're on these days, but where we talked about, obviously when we're doing the ICR and there's the elderly person that's had the quote for thousands of pounds and is then worried about the condition of their system. If they've got an old system that has absolutely no sign of overload, no sign of excess use, an immaculate 3036, back in the 17th, I would mount an RCD unit adjacent to that. And I wouldn't put them under any further stress. But nowadays, with AFDDs in the future, because you want to make sure your work is future-proof, and SPDs, 3036 boards, as long as it's affordable, it would be recommended to replace them so they can accommodate more modern technology, because it's just not practical on a 3036 board anymore. But they are still within BS7671, so we can't say they don't comply. And we can't say without evidence that they're dangerous. It's more a case of, okay, advising the client as to how technology has moved along and how the new technologies just don't necessarily comply. They just don't fit in that current board makeup. And that's the point, you know.
My golden rule is that if I've always leave the installation safer than I found it. Now, if they can't afford a new board, if they need to keep the rewirable board because they can't actually afford a new fuse board, then I'll just do what I can to make it safe within the budget they've got. You can recommend and you can give people advice and you can give people all sorts of information, but if their budget, if they haven't got the money in the bank, they're not going to change it. So rather than walking around and saying, I'm not working for you because you're not spending money, I would do what I could for them within the budget they've got, but I would make sure that I've reported everything and it's all down on paper. Ben's talked there about a QS changing coding on an EICR.
Yeah, that's the question I was going to have at the end. That's I was going to put my, but you've mentioned it, so yeah, okay. So he's got a query. What are your thoughts of a company's QS changing your codes?
How the hell do they know how to code something if they haven't actually been out physically to go and look at it? This is the thing that really cheeses me off. The QS sits in an office, doesn't actually go to look at the installation, and then goes to alter the codes or the information that the inspecting engineer has actually put on there. It's wrong. You cannot, if you're sat on your backside in an office, you cannot alter somebody else's paperwork
Yeah, but even if
nonsense.
even if the QS is proactive and about, they cannot force you to change your inspection decisions. If you're a competent inspector, their job, it's a bit like in the training industry. We have assessors and we have internal quality assurance. You know, assessors make assessing decisions. An internal quality assurer cannot overrule that, but they can assess the quality of that. You know, and that's just the point, and that's what QS is supposed to do, really determine the quality of the inspector. And if QS keeps having to get involved and adjust things and change decisions, the inspector isn't doing the right job. And it's not QS's job. I mean, if you think about it, I mean, we have on the EIC, we have the signing for the inspection, we have a reviewed by. That's what the QS is. It's a glorified reviewer of documentation.
Yeah.
Make sure it's to a quality standard. They can't make the inspector change the inspector's decisions. They can pull the inspector aside, do a toolbox talk, offer a bit of information. It'll then be up to the inspector to go back and change his decisions or her decisions. The QS cannot change that data.
Well, it relates back to the discussion we had earlier over the fire thing. Is that what will happen sometime is that the inspection engineer will go and do an inspection and sort of say, oh, okay, this is what I found and this is how I'm reporting it, and they'll code it. It goes back into the office and the QS will sit there and think, oh, I don't want to upset that customer. I'll change that C2 to a C3.
Yeah.
So it doesn't make their installation unsatisfactory. I mean, that is just crazy. You know, it's as an inspection engineer, if you're producing documentation, make sure you keep a copy of what you do. And then if some buffoon does change it in the office, then that's their call, and you can at least say, well, look, this is my document. So when the house burns down later on and you're all pulled into court, you can say, well, this is how I reported it. That numpty over there changed it. Yeah, so nothing was done about it. This is my report. He's changed it to that. Blame him. And unfortunately, this is the ball game we're in sometimes. Yeah.
Okay, Jamie says, would you recommend the Mega Cable Sizing app? I've checked against the regs and it is accurate. The most important thing is the last thing you said there, Jamie. There's lots of apps, softwares, there's many good programs, there's many poor ones. You must be able to check it yourself, because if we end up relying on them, creating the outputs of information we then put our name to, then, you know, it might be that there's an update that's lost, there's some error in the code, or, you know, there's one fairly well-known one recently that's had some major trouble. So always make sure you're revising your own ability to reverse engineer the calculations that software is supposed to do. And now and then, test it yourself. Say, I'm going to tell it something, it should give me this. If it does it, you know it works. So always check by yourself and always make sure you are happy in your own competence to verify that and check it. Yeah. And then it can do it as a tool for you. It shouldn't make decision-making processes for you. And I say this all the time, all the software is only as good as the inputs that you put into it. And if you don't know how to put in the inputs, then you can't rely on its outputs.
Yeah, I mean, that actually, the only thing I'd add to that is if you look at Lawrence's question, talking about other than the 30% rule, right, are there other situations where you don't have to use other grouping factors? It's the same with all of this business of applying factors for different reasons when you're doing cable calculations. If you have assessed the situation and how it's being used, different installations, you go to so many different places, they're used differently, they've got different firms, they different types of users, they've got different patterns of use, all sorts of different environments. You've really got to look at these things and say, okay, fair enough, how am I going to assess this? Okay, so it's just simply going by all the factors in the regs doesn't always work. So sometimes you might look at a group of cables and you know, because of the way the business is being used or the premise is being used, you know that some of those cables are not going to be on at the same time as other circuits because of the way the place runs. So you can then take an engineering view and judgment, and you can then decide, okay, I'm going to adjust this factor to this level, okay, and just write it up and include that in your report. This comes back to what the other guy was saying about using the mega cable calculation thing.
Jimmy,
if there's room in there to actually apply a slight alteration to that, fantastic, yeah. But if it's an app that just bog standard chunders through the same old sort of calculations all the time without you being able to make any adjustment by an engineering point of view, then you've got to consider that. Yeah, I don't like things that are just bang, bang, bang. We'll just regurgitate the information that's in the book. All right. We always need to apply our own decisions, our own point of view to these things, and that's the rule I take.
Yeah. No, I mean, you mentioned, it's important for us to understand the use. I mean, you may have distribution in one wiring system that was initially designed that it's only one or the other. So it could even be at the end, you have a switch that allows the supply to be taken from one or the other so that they are protected from being on simultaneously. It's just important, again, with inspections, that we have the time. Cheers, Bray. Catch you later. That we have the time to collect that understanding on again, I've said utilization in so many webinars. The utilization of the electrical installation. Instead of arriving, ways you've used, we'll count the circuits, measure ZSs. It's, okay, what do you do? How do you do it? How often are you busy? Just stand and observe. Absorb all the use of the building and the system. Get an understanding on its engineering principles, its behavioral characteristics. Even look at the competency of the users to see if they actually are suitable to use the specific switchgear or control gear. There are external influence categories for the utilization of equipment. Unfortunately, none of this is written down as test data. So a lot of us are stressed out not to actually and can't do that because we're paid for the values we put on a piece of paper. Jamie then has just said he's not sure if the app takes a consideration of the rating factors, CA or CI. If it's a cable calculation, it would have to have some level of information to request something. I'll check it. I've not tried it out, Jamie. I'll have a look.
I've not used it. I must admit, I haven't seen it. I haven't used it. I'm old school.
Old school. There must be some questions it asks about something. Okay.
Mark's talked about different cable ratings. If you've got a conductor,
okay.
So like in the book, you can have 60-degree insulation. You can have 90-degree insulation. Why would you choose 60-degree insulation when you've got cables that have got 90-degree insulation? So you can end up using a cable which has actually got a smaller CSA, which is probably going to be cheaper and easier and lighter to lump around, rather than going for the 60-degree C, where you might have to end up buying a larger cable. Yeah, I totally agree. And I would, in preference, when I can, I'd use an XLPE at a higher temperature rating, which will minimise my cable size. It's normally actually cheaper because you obviously got a smaller conductor size, and it's lighter. And let's face it, the lighter the cable, the smaller the cable, the easier it is for us to terminate and to lump around. And I like that. I'm getting too old to lump big cables around.
I've done some recent duty holder work with a company that manufactures servos, and they manufacture all these little, this wonderful line where I saw the transformers and I saw everything being manufactured, but their cabling is quite small, but it has, I think, a 120-degree limiting temperature. And that's what they've done. They've got this specialist cable in. It wasn't thermoplastic or thermostatic. It was something else. I can't remember. I've got it on a file that I saved. But it has a limiting temperature of 120, which meant the cables can be smaller and they can be grouped more effectively. And that was a suitable selection decision for them to manufacture stuff. Again, it's the importance of us looking for the information, and the information should always be made available.
There's a question about CPD accreditation there. We've been talking about this for a while. The problem with CPD accreditation, from our point of view, we've been to various companies, is that some of these registration companies, as they call themselves, want £1,500 plus VAT for us to actually register these as CPD accredited. There are other ways, and to be honest, you don't need to go to these companies for CPD accreditation. Everything you do is CPD. If you read a book, read an article, watch a video, it's all CPD. So it's down to individuals to record it. However, we are looking at some other ways of recording things officially and getting CPD done. So watch this space. We will do what we can.
Yeah, I mean, some people have been very generous by donating and stuff, and all of that has gone towards raising some money to get this all CPD accredited. Unfortunately, we've approached them, and these companies all accredit a course. So a company will create a training course, and they'll redeliver that as many times as they want. What we're trying to do is find a way to structure all of this to be as fewer accreditations as possible, because they would like us to pay them £500 for this one, £500 for the other, and so with the number of subjects we've done, you're looking at £5,000. And so it was just, and it's non-starter from the beginning. So we are in communication with a couple who are trying to come up with some solution, because fundamentally we know that some of you guys do work for employers that want to see CPD accreditation third party on these things, and we'll do our utmost to try to get it. And if we can get an arrangement done, that's the first thing we're going to do with all the money that's been donated. Unfortunately, it's just because we've delivered so many subjects and things. We want to deliver more subjects. We don't want to be restricted. We want, we want to do workshops. We want to do what we've had today. We've had RCDs recommended. We've had coding recommended. We've got a list of about 7 or 8 other subjects just last night we come up with. We want to do more different subjects so we can keep ourselves thinking. The creditors go, that's another £500. That's another £500. We're looking for it. We're looking for a solution.
Yeah. It's the annoying thing. We say to these accreditation companies, say, look, we're doing this for nothing. This is all free stuff, free content for the guys. We're trying to keep everybody busy, trying to keep people's brains going over in this period of time. We're trying to do this for, all sorts of reasons. And we're doing it for nothing. So is there anything you can do for us? No. 1,500 quid for five subjects.
1,500 quid is up to 5, and then every other one is like £300 or £400.
Yeah, crazy.
Depending on how it does. But yeah, we'll see. We'll do our best. Look, if we don't manage to get anything, we'll get a cert sent out anyway. I've got a cert designed. We've got it done. It's just a case of I'm trying to hold off so that I can send it with something badged onto it, so that you guys can obviously get, don't get any questions from your employers, etc. Watch this space. There will be certificate regardless, but it's a case of if we get a CPD badge on it, we're right now trying to find something that is financially suitable.
Right, Emma, we'll put that on the list.
Standby power.
Yep, we'll put that on the list.
Anything specifically? Are you thinking of standby UPS systems or standby generators, or all of the above?
Integration of the two. Yep.
UPS and generators. Okie dokie.
Yeah. Is it for things like data centers or that sort of stuff?
Yeah, okay.
Yeah. All right, we'll look into that. We know some people that might have some good information on that. Data center and healthcare. Yeah.
Data center and healthcare. Yep. Thank you. Okie dokie. Yep.
Okay.
All right. Was that all the questions? And there's one more. Jamie's squeezed one in at the very top there. Cheers, both. Asks you load, cable type, reference method, voltage, cable length, and it gives you a minimum cable size, volt drop, percentage drop, and load. So load, cable type, reference method, voltage, cable length.
Yeah.
So it doesn't ask anything about the factors. That's This is the mega one. Is that right, Jamie? I'm going to download that and have a look-see.
We'll have a look. Have a play with it.
I'm actually on the phone to Lee straight after this webinar from Mega. So I'll have a check and then I'll be on the phone to him, because I'm on the phone to Lee this afternoon. Right.
Thank you, Daniel.
All right. Start at 3, finish at 6. That's a potential danger there, Lawrence. All right. I still struggle to find this end meeting button. How long have I been doing this now? Right.
Take care, guys. Look after yourselves.
See you later, guys. Bye-bye.